In the previous lecture, we have to started to discuss the basic theory of superconductivity, which is a quantum mechanical theory and very successful in explaining all the properties of superconductors. Okay, and you know that theory was actually BCS theory. And as I have told you that in these two lectures we will see only the basic ideas provided in this theory in a qualitative manner, not in a quantitative manner. After this second lecture on BCS theory, we will see the quantitative calculations of this theory, and then our concept regarding this BCS theory will be very clear. Okay. Actually, in the first part of the lecture on this BCS theory, I have told you that in 1957, this is just a repeated thing, three scientists, Bardeen, Cooper and Schrieffer, provided a microscopic theory of superconductivity, and this theory is popularly known as BCS theory. And as I have told you that this is a most successful theory and it explains all the properties of superconductor only except those of high transition temperature ceramic superconductors. Okay, and for this work these three scientists got Nobel Prize in 1972. This fact I have actually stated in our first part of the lecture too. Actually, we are going to see the explanation or the idea of four facts regarding a superconductor or superconducting state in this theory, and those are electron phonon interaction, another is Cooper pair, and after that existence of energy gap and BCS ground state. And in our first part of lecture you have already seen the explanation of this electron phonon interaction and this Cooper pair too. Now in today's lecture we are going to explain the existence of energy gap and BCS ground state. Okay, so actually these two basic ideas we will see in this present lecture. So first of all we are going to see the existence of energy gap. You know, in a normal metal there is no energy gap, there is no forbidden energy gap between the conduction band and the valence band. That is almost zero. But when a metal is transformed into a superconducting state, then energy gap actually exists. Okay, and this energy gap is a basic feature of the superconducting state, which actually explains several electromagnetic properties and thermal properties of a superconductor. Okay, so actually how this energy gap exists we will see. In fact, you have seen in first part of the lecture that due to the phonon mediation, a pair of electron is formed due to the attractive interaction between the electrons, which is called Cooper pair. Okay, and actually this attractive interaction between electrons leads a ground state of the entire electronic system, which is separated from the excited states by an energy gap. So there will be a BCS ground state and there will be also an excited state, and the difference of the energy of the excited state from the ground state, that is called energy gap. Okay, In fact, the Cooper pairs are bound together by a very small energy uh, which is denoted by the symbol delta, which is called energy gap parameter. And these Cooper pairs actually form a new ground state, which is in fact in nature superconducting. And this ground state is separated from the next lowest excited state above it by an energy gap which is given by Eg equal to 2 times of delta, where delta is actually the gap parameter. So actually uh, definitely an energy gap will appear in all the superconductors. Okay, and you can see here in this figure I have shown a superconducting state of the matter, and this is the uppermost level of the field band. When you say that this is the field state, it means you are talking about the BCS ground state. This is BCS ground state. Okay, and this state is actually superconducting in nature, and this state is actually an excited state. Okay, excited state, and you can see from this figure that the ground state and the next excited state is separated by an energy gap given by this Eg, which is equal to 2 times of delta, where delta, you know, it is called energy gap parameter. Okay. In fact, the Fermi level, which I have marked here by this dotted line, this Fermi level EF lies just in the mid of this energy gap. Okay. In fact, if you are talking about this delta, which is called energy gap parameter, for a material like gallium, it is given by 1.4 times K times Tc, where K is actually the Boltzmann constant. And for not be confused, I am writing here a subscript B so that it will be obvious that it represents Boltzmann constant. And Tc is actually the transition temperature or the critical temperature. And when you will put the value of Tc for gallium, and Kb is a universal constant whose value is already known, then it comes out almost to be equal to 10 to the power minus 4 electron volt. Okay. In fact, the electrons present in the excited states, all those electrons which are present in this excited states, behave just like normal electrons. Okay, and these electrons actually create the resistance. Okay, and so when the current is passed through the material, it experiences resistance due to the electrons present in this excited state. But when you will talk about the electron below this energy gap, okay, which is actually in this BCS ground state, these electrons are of superconducting nature. Okay, so you can say that the electrons present below this energy gap are actually superconducting electrons. Okay, and they will not offer any electric resistance in the flow of electric current. Okay. In fact, it is found that the energy gap varies with temperature. When temperature is changed, then the value of this Eg will also change. In fact, it is maximum when temperature is absolute zero. Okay, and you can see this figure when temperature T is equal to 0 Kelvin, then the value of this energy gap is actually maximum. You can see I have plotted here a graph between the energy gap delta at temperature T over the energy gap at 0 Kelvin temperature in against of T over Tc. Okay, so this is just a graphical plot of what? This is a graphical plot of energy gap in against of temperature T. And you can see when T is equal to 0 K, then it's the value of this ratio is equal to 1. It means it is highest. And when T is equal to Tc, you can see here, then actually this energy gap becomes 0. Okay, at 0 Kelvin temperature, when the temperature is not 0 Kelvin but temperature is equal to Tc. So when T is equal to Tc, then this delta vanishes. Delta is 0. And if delta is 0, Eg will be also 0 because this is 2 delta. Okay, and between T equal to 0 and T equal to Tc, you can see this energy gap continuously decreases, just like in a parabolic fashion. Okay, so in fact it is found that the value of energy gap is maximum at 0 Kelvin temperature, and it decreases continuously to 0 as the temperature is increased to the critical temperature, as you can see in this figure. Okay, so you can say that at 0 Kelvin there are no electrons above the gap, and at T equal to Tc all the superconducting electrons become normal electrons. Okay, and due to the presence of energy gap, the superconductors respond to high frequency electromagnetic radiations of particular frequency. And so you can say that the energy gap is a characteristic feature of all superconductors which determines their thermal response to high frequency electromagnetic fields. Okay, so this the existence of an energy gap is in accordance with our BCS theory. So this and the existence of energy gap is an important consequence of BCS theory, as you can see. Okay, now we will learn about the another basic idea of this BCS theory, and that is regarding the BCS ground state. Actually, what I have explained, I have written here for your convenience. You can note down these things in your notebook, and that will be very helpful for your examination purpose. Okay, now see, now we are going to see the important a very important idea which was which we can find from this BCS theory. And for this, let us see first of all this figure. In this figure, actually I have shown the ground state of non-interacting Fermi gas and the ground and the BCS ground state in 3 dimensions. Okay, actually the BCS ground state which has been shown in this second figure, you can see, differs from the ground state of non-interacting Fermi gas as you can see in this figure A. In fact, when you say the ground state of non-interacting Fermi gas, it means you are talking about the free electrons present in a metal when the metal is not in the superconducting state. because you know free electrons are just fermions, and they behave just like a gaseous system which is called Fermi gas, because those electrons obey the Fermi Dirac statistics. Okay, you can see that in case of the non-interacting Fermi gas, all the states below the Fermi surface are occupied and all above it are vacant. Actually, this surface which I have shown this figure, you can see that this represents the Fermi surface of energy EF in case of the non-interacting Fermi gas. And these the region uh, below this Fermi surface, I have shaded this region, and this shaded region actually represents that these states are actually completely filled. Okay, and the electrons in these states are in ground state. Okay, and above this Fermi surface, in case of this non-interacting Fermi gas, there is no electron, all the quantum states are vacant. Okay, all the quantum states are vacant. Okay, but when you see the BCS ground state in this figure, you can see the lowest excited state is separated from the ground state by an arbitrary low excitation energy. That is, one can form an excited state by taking an electron from the Fermi surface and raising it just above this surface, because here this is the ground state and here is Fermi surface. So in between these two regions there will be electron which will be in excited state. Okay, as we have learnt earlier that the phonon mediated attractive interaction between the electrons give rise to the BCS ground state, which is actually superconducting. Okay, this state is separated from the lowest excited state by a finite energy gap Eg, we have learned, and the formation of BCS ground state you can understood by seeing this figure. Actually, you can see that the BCS state appears to have a higher kinetic energy than the Fermi state, but the attractive potential energy, which actually have not shown in this figure, the BCS state acts just to decrease the total energy of the BCS state relative to the Fermi state. Actually, in this figure, you can see that the probability occupation of one electron state of electron has been plotted in against of the energy. In first figure A, you can see the ground state of Fermi gas, and in second figure in the ground state of BCS gas. What is actually the remarkable difference between these two, you can see. Actually, the BCS state is more stable than the Fermi state, and superconductivity actually persists. The occupancy of one particle, orbitals or quantum states near this EF, you can see near this EF in the BCS state resembles somewhat like the that obtained from the Fermi Dirac distribution function at a finite temperature. However, in the BCS state, the one particle orbitals are occupied in pairs which are called Cooper pairs. Okay? If an orbital with wave vector k, you can see I have written it here, that if an orbital with wave vector k and a spin up is occupied, then one with wave vector minus k and a spin down will be also occupied. And in this likewise, you can say that if k up is vacant, then minus k down will be also vacant. Okay, so these ideas were actually we get from the BCS theory, And now, as I have told you, that these were actually the only the qualitative discussion of BCS theory. In our forthcoming lecture, we will see the quantitative approach to explain this theory. Okay, thank you very much.